All right. Hey, everyone, and welcome to Machine Learning and Fairness. So I'm Hannah, and Jen is here in the audience. She's going to come up in a couple of minutes. And we are both machine learning researchers in Microsoft Research, New York City. And since most of you don't know us, I wanted to take a minute or so just to tell you a little bit about who we are and what we do. Okay, so as I said, we're machine learning researchers, and we've each been doing machine learning for about 15 years at this point, working on a mix of theoretical and applied projects, often in collaboration with social scientists. Over the past 4 years, though, we've both become increasingly interested in fairness, accountability, transparency, and ethics as they relate to AI and machine learning. We're both members of Microsoft's FATE research group, which was formed in 2015 to focus on exactly these issues. It's an inherently socio-technical group with core AI and machine learning researchers like Jen and myself, and researchers in the social sciences, policy, and the law. Jen and I are also both very involved in Microsoft's AI and Ethics in Engineering and Research Committee, or ETHA, where I co-chair the ETHA Working Group on Bias and Fairness, and Jen co-chairs the Working Group on Intelligibility. Okay, so I want to start by talking about AI and machine learning. So as you all know, machine learning is super hot right now. And over the past 15 years or so, we've seen machine learning go from some weirdo academic discipline only of interest to machine learning nerds like me, to something that's so mainstream that it's mentioned on billboards and even appears in webcomics and TV shows. If you don't believe me, this graph shows the number of registrations for the largest machine learning conference, Neural Information Processing Systems, or NeurIPS for short, from 2002 with around 600 registrations to 2018 with 8,500 registrations that sold out in 11 minutes and 38 seconds. Yes, really. So at the risk of stating the obvious, we're living in the age of AI. Machine learning is everywhere, and at least for now, it looks like it's here to stay. And this is great. It means there are some amazing opportunities for researchers like me and Jen, for people with practical machine learning skills, and for companies like Microsoft. And indeed, to put Microsoft's mission statement into practice, we're definitely going to need AI and machine learning. But at the same time as all this excitement, we're seeing that these new opportunities also raise new challenges. Challenges that have received a lot of attention in the media and have really highlighted how important it is to get AI right, to make sure that AI does not discriminate or further disadvantage already disadvantaged groups. Many of these stories have focused on high-stakes decisions where machine learning systems are used to allocate opportunities, resources, or information in ways that can have significant negative impacts on people's lives. So, for example, a couple of months ago, Amazon revealed that it had abandoned an automated hiring system after finding that the system amplified gender bias in the tech industry. Or, as another example, I'm sure many of you heard about the ProPublica investigation a couple of years ago, which showed that Compass, a widely used recidivism prediction tool, was, according to some metrics, racially biased. These biases can also affect more mundane systems too. For instance, in 2013, LaTanya Sweeney showed that online ads suggesting that people had been arrested appeared more often for distinctly black-sounding names than for other names, thereby reinforcing negative stereotypes of black criminality. So how do these stories relate to fairness? Well, broadly speaking, they're all examples of machine learning systems causing harms to some people but not to others. So in other words, examples of machine learning systems behaving unfairly. Of course, and this will be a recurring theme throughout this talk, fairness is a fundamentally societal concept that's been studied by philosophers, lawyers, and social scientists for hundreds of years. Moreover, there's no one-size-fits-all definition of fairness that's suitable for all systems in all contexts. So it's a bit daunting to be suddenly grappling with fairness throughout the tech industry. That said, at least as we see it, we're not completely unprepared. In particular, we can think about fairness in a similar way to the ways that we think about security and privacy. First, security and privacy are both socio-technical challenges, as is fairness in the context of machine learning. Sure, fairness is a little closer to the socio end of the spectrum, but they're all on there. Second, in the tech industry, security and privacy are much older topics than fairness, so we can really learn a lot from their history. In particular, in the late 90s and early 2000s, security and privacy efforts were very competitive, adversarial, and closed door. And this was driven by companies' fears of public criticism, negative press, and financial costs, and by the assumption that it would be possible to eliminate security and privacy incidents. As a result, the focus was very much on prevention and detection, often post-deployment. During the 2000s, though, this landscape changed considerably, and in fact, Microsoft was a leader in this change. Companies began to realize that there was value in collaboration, cooperation, and openness, and began working together to prevent and detect vulnerabilities. Now we've reached a point where the tech industry acknowledges that it's impossible to eliminate security and privacy incidents. Of course, this doesn't mean that it's not worth investing resources into prevention and detection, but we must be prepared for such incidents to occur, and must therefore also prioritize and invest resources into responding appropriately. I think that we can learn from this and approach fairness with the same emphases on collaboration, cooperation, and openness. Of course, we need to prevent our systems from exhibiting biases as best we can, but we also need to respond appropriately when they inevitably do. To put it differently, we need to adopt a growth mindset toward fairness. Just as security and privacy aren't one-shot processes and require continual evaluation and improvement, fairness isn't a one-shot process either. We will make mistakes. Let's therefore anticipate them as best we can, but when they do occur, let's turn them into something positive. Specifically, let's learn from them and use them to improve our systems and contribute to our successes. Okay, so with that background out of the way, we're going to cover 4 topics today that will collectively give you an overview of fairness in machine learning. We'll start by talking about some of the main types of harm that can occur so that you'll know what to look out for in your own systems. Then we'll talk a bit about who might be affected by these harms. So in other words, which groups of people or subpopulations might be most at risk. Next, we'll run through where these harms come from, focusing on the different stages of the machine learning pipeline. And at each stage of the pipeline, we'll talk about best practices and strategies that you can use to mitigate the harms that can arise at that stage. And then finally, we'll talk about some recently developed software tools before concluding with a handful of open questions and key takeaways. Okay. Types of harm. So I want to note that the next few slides are based on a framework for characterizing types of harm by Aaron Shapiro, Solon Barocas, Kate Crawford, and myself, though I've modified the framework a little bit here. Broadly speaking, there are 5 main types of harm that can occur in a machine learning system: allocation, quality of service, stereotyping, denigration, and over or underrepresentation. To explain each of these 5 types, I'm going to run through some illustrative examples, starting with the most well-known type, allocation. But before I do that, I want to note that these types are not mutually exclusive. It's possible for a single system to exhibit more than one type of harm. And indeed, many of the examples that I'll show you over the next few slides could potentially illustrate one or more of the other types as well. So first, allocation. As I said earlier, many of the recent stories in the media have focused on high-stakes decisions where machine learning systems are used to allocate opportunities, resources, or information in ways that can have significant negative impacts on people's lives. So, for example, Amazon abandoned its automated hiring system after finding that the system amplified gender bias by withholding employment opportunities from women in the tech industry. Similarly, the racial bias found in the Compass recidivism prediction tool is also a harm of allocation, because among defendants who ultimately did not reoffend, Black defendants were much more likely to be classified as high risk than white defendants, and thus denied the opportunity of being released on bail. Quality of service is all about whether a system works as well for one person as it does for another, even if no opportunities, resources, or information are extended or withheld. So, for example, last year, researchers found that 3 commercial gender classifiers had higher error rates for images of darker-skinned women than for images of lighter-skinned men. Much like accessibility issues, harms relating to quality of service also raise questions about respect, dignity, and personhood. Imagine how a user might feel if a system repeatedly fails to recognize her voice, but easily recognizes those of her peers. As a second example of a harm related to quality of service, virtual reality systems often make women feel sick, while men seem to be largely unaffected. Okay, stereotyping. One of the most well-known examples of stereotyping in machine learning is the example I mentioned earlier, where online ads were more likely to suggest that people with Black-sounding names had been arrested, thereby reinforcing negative stereotypes of Black criminality. In a similar vein, researchers at Princeton found that translating "he is a nurse" and "she is a doctor" into Turkish, a gender-neutral language, and then back into English, yields the stereotypical "she is a nurse" and "he is a doctor." And just to be clear, this harm was not unique to Google Translate. It affected Microsoft Translator and other machine learning systems too. And Google actually came up with a really creative way to address this harm just last month. Denigration is where a machine learning system is itself part of a process that is actively derogatory and offensive. So, for example, a couple of years ago, Google Photos infamously mislabeled an image of a Black woman as gorillas. This mislabeling is offensive not just because the system made a mistake, but because it specifically applied a label that has a long history of being purposefully used to denigrate and to demean people, to liken them to animals. As another example of denigration, Microsoft had to shut down the chatbot Tay shortly after it launched because it started generating hate speech. Over and underrepresentation are fairly self-explanatory, but as a concrete example, researchers at the University of Washington found that professions with an equal or higher percentage of men than women for image search results were even more heavily skewed toward images of men than reality. So then to recap, the 5 main types of harm that can occur in a machine learning system are allocation, quality of service, stereotyping, denigration, and over or underrepresentation. Before I move on, I want to again reiterate that these types are not mutually exclusive. A single machine learning system can certainly exhibit more than one type of harm, as I've tried to indicate here on this slide. All right, great. So we've covered different types of harm. Next, I'm going to talk briefly about who might be affected by these harms. So in other words, which groups of people or subpopulations might be most at risk. In general, the machine learning literature typically focuses on subpopulations that are protected by law, such as race, gender, age, or religion. In practice, though, there are many subpopulations that we might wish to be fair with respect to, and it's not always easy to identify the most relevant ones. Last summer, Jen and I, along with our colleagues Hal Daume and Miro Dudek, and our incredible intern Ken Holstein, conducted the first systematic investigation of industry teams' challenges and needs for support in developing fairer machine learning systems, which will be published at this year's conference on human factors in computing systems. We found, among other things, that practitioners expressed needs for support in identifying which subpopulations to consider when auditing their systems for biases. Some practitioners also noted that the most relevant subpopulations may even be application-specific. With permission, I'll read you a quote that illustrates this point from a practitioner whose team develops general-purpose machine learning tools. People start thinking about sensitive attributes like your ethnicity, your religion, your sexuality, your gender. But the biggest problem I found is that these cohorts should be defined based on the domain and problem. For example, for automated writing evaluation, maybe it should be defined based on whether the writer is a native speaker. It's also really important to consider intersections of populations. The case of Emma de Graffenried versus General Motors is a really great example of why. So in 1977, Emma and several other black women sued General Motors for discrimination, arguing that the company segregated its workforce by race and gender. General Motors pushed back, claiming that they hired black people and they hired women. However, digging further into the data revealed that all the black people they hired were men who worked in warehouses, while all the women they hired were white and worked as secretaries. So in other words, only by considering the intersection of race and gender was it possible to show that General Motors was indeed discriminating against black women. One obstacle to detecting and mitigating harms that affect particular subpopulations is access to relevant attributes. The machine learning literature generally assumes access to these attributes at the level of individuals. However, many teams have no such access and instead rely on coarse-grained, partial, or indirect information. One way around this is to ask users to report relevant attributes, purely for the purpose of auditing systems for biases. However, this can raise privacy concerns, especially in light of the European Union's General Data Protection Regulation, or GDPR. And some users may object. Another option is to try to infer the relevant attributes from other available data sources, though this can introduce new biases, and again, users may object. Sometimes the subpopulations that we wish to be fair with respect to are defined in terms of social constructs, which makes accurately measuring relevant attributes especially hard. For example, race is a social construct, one that depends on geography, context, and even time. Moreover, two people can both identify as the same race, but have very different physical characteristics. Therefore, in the context of a computer vision system, for example, it may be preferable to consider fairness with respect to skin tone, an easily measurable attribute, rather than race. As well as being observable, skin tone is also more likely to affect the performance of a computer vision system than race per se. So before I move on, I do want to note that although this talk focuses on fairness with respect to particular subpopulations, this is not the only way to think about fairness. For example, some machine learning papers focus instead on individual fairness, or treating similar people similarly. And while this is intuitively appealing, this approach generally requires the ability to define some quantitative notion of similarity between individuals. In practice, though, this can be challenging to do accurately, so we're not going to cover individual fairness here today. Another way to think about fairness is in terms of counterfactuals. So, for example, would I have been hired if everything about me were the same except for my gender? Again, this approach to fairness is intuitively appealing. But, as Isa Kohler-Hausman points out, it's not possible to manipulate race or gender in this way. Even putting aside practicalities, you can't just flip someone's gender and assume that nothing else about them would change. For example, my personality and characteristics are all heavily influenced by my lived experiences as a woman, and so it's just not realistic to expect that I would possess the same personality and characteristics if I had instead been born a man. So for this reason, we're also not going to cover counterfactual fairness today. Great. So with that, I'm going to hand over to Jen for the next part of this talk.
All right. Okay. So hello, I'm Jen Wortman-Vaughan. In the last few minutes, Hannah's walked us through different types of harm that can arise in machine learning systems and which groups of people are most likely to be at risk from these harms. So I am now going to spend the next chunk of time discussing where these harms come from and at the same time, strategies that you can take to mitigate these harms. I want to emphasize from the very start of this portion of the talk that fairness is not something that can be treated as an afterthought, and it needs to be considered throughout the entire machine learning pipeline. If you walk away from this part of our talk remembering one thing, I hope it's that. So a typical machine learning pipeline looks something like this. We start by defining the task or problem that we'd like to solve. We next construct a data set. Data set construction involves selecting a data source, acquiring the data, pre-processing the data, and perhaps labeling the data. Third, we define a model. Are we going to use a linear model or a decision tree or a neural network? What is our objective function? Each of these choices is associated with its own set of implicit assumptions. Fourth, we train the model on our data. We next test and validate the model before deploying the model in the wild. And finally, we gather feedback about the performance of our model in practice and use this feedback to improve the system. We'll see that decisions that are made at every point in this pipeline can introduce bias. So let's start at the beginning with the task definition itself. What is the problem that you are trying to use machine learning to solve? So as one extreme example of what can go wrong here, in 2016, a research paper came out by a group in China who were training a face recognition system to predict who is going to commit a crime based on images of people's faces. This is extremely concerning for a whole suite of reasons and could lead to substantial harms for people who are misclassified. I hope it goes without saying that this is a questionable and rather sketchy task design, and I would argue that this is not a task that machine learning should be used for, period. But there are more subtle examples too. Consider the problem of gender classification, predicting someone's gender from a photo. On the surface, it might be less clear what are the potential harms here, but there are a couple of potential issues that come up. So one is that a gender classifier would generally only predict binary gender, so it won't work at all for people whose gender is non-binary. Gender classifiers also reinforce societal stereotypes about how men and women are supposed to look. In fact, the way that a system like this would probably work is actually by exploiting these very stereotypes. It will therefore only work well for people who look like typical men or typical women. Finally, it's often best not to force a gender label on somebody without asking them themselves in the first place. There are steps that we can take to mitigate harms during the task definition stage of the pipeline. First, clearly define your task and the model's intended effects. Taking gender classification as an example, the task here is to classify people as male or female using images of their faces. The intended effect is for people who look male to be classified as male and people who look female to be classified as female. 2, try to identify any unintended effects or biases. You may need to do some reading here. Are there known biases for this particular task or domain? For gender classification, one unintended effect could be that people who don't look like gender norms could be misclassified. When thinking about unintended effects and biases, think about how others might take the output of your system and use this, and what systems your output may be feeding into. 3, make sure to involve diverse stakeholders and multiple perspectives to try to uncover unknown unknowns and blind spots in your system. In our example, involving diverse stakeholders might reveal that non-binary people are underrepresented and will likely suffer from poor quality of service here. Next, be willing to redefine the task if you need to, or even willing to abort in extreme cases. In our example, you might first consider adding additional labels beyond male and female. But through conversations with diverse stakeholders, you may realize that the system actually relies on stereotyping at its very core. If misclassifications are too costly, you may decide to just give up on the project. Finally, if you do decide to proceed, document any unintended effects and biases so that you can keep referring back to them and checking for them throughout the rest of your development process. Sometimes task definitions change and evolve over time, and biases can end up being reintroduced later in the pipeline. Okay, let's move on to data set construction. So I'm going to spend a bit more time on this phase of the pipeline than the others because it's very common for biases to creep in here, and there are a bunch of different ways that this can happen. So one way that this can happen is that the data source may reflect societal biases. The world has a lot of bias in it, and our data sets usually reflect the world. This is what happened when Amazon tried to build the machine learning-based recruiting tool. If your data source contains mostly male resumes and you've historically hired mostly men, your machine learning system is going to pick up on this. Linguistic bias is also a problem. People are more likely to say she is a nurse than he is a nurse. So as Hannah discussed before, a translation system trained on text or speech that's generated by people is going to prefer that translation. Bias can also arise if data is collected from a skewed source. So if we train a face recognition system on images of mostly white men, then it will likely work well for white men, but maybe less well on other populations. As another example, the city of Boston released a smartphone app called Street Bump in 2011. The app would monitor for bumpiness caused by potholes when people were driving down the street and report these potholes to the city so that they could then be repaired. On the surface, this seems like a really great idea. The problem was that back in 2011, smartphones were much less prevalent than they are today. And so the people who used the app tended to be younger and more affluent. As a result, the potholes that were reported were much more likely to come from wealthy neighborhoods. Luckily, the city did eventually become aware of this problem and quickly acted to counteract it. Skewed samples can also arise due to the backgrounds and cultural biases of the people involved in the data collection process. For example, during the interviews that we conducted with machine learning practitioners, which Hannah mentioned earlier, one team reported that they had trouble collecting images of celebrities that were popular in other countries simply because nobody on their team happened to know what these celebrities looked like. So in order to mitigate harms that arise when selecting your data source, you should think critically about potential biases before actually collecting any data. Check for biases in the data source selection process. Before building their recruiting system, Amazon could have carefully considered their data source and realized that it was problematic since there are fewer women in tech jobs and the data would be heavily skewed male. Try to identify societal biases that are present in your data source. We know that there are more female nurses than male nurses, and that people are likely to talk about nurses in a gender stereotyped way. So this is a bias that, again, could be identified in advance. Fourth, check for biases in the cultural context of the data source. And finally, you should check that the data source matches your expected deployment context. And this is something that I'll come back to again a little bit later. In terms of the process of actually collecting your data once you've identified your source, you should check for biases in the technology used to collect the data. thinking through potential biases in the technology could have more quickly identified problems with the use of the Street Bump app. Check for biases in the humans involved in the data collection process. This can catch cases where a team doesn't have the proper cultural background to gather the data that they need for some system. Next, if sampling data points from a large population, check for biases in the sampling strategy and assure sufficient representation of subpopulations. Following these two best practices would have flagged the skewed data sets that many face recognition and gender classification systems were being trained on. Finally, check that the data collection process itself is fair and ethical. This one can be tricky. Even if we know that we need more data from a certain subpopulation, there's this question of how we can actually ethically collect it. The challenge is to avoid putting a tax on already disadvantaged populations. For example, by forcing all of our coworkers who are from some minority population to come and supply data for us on every product that we're building. Yet another way that bias can arise in dataset construction is through labeling and pre-processing. For example, there's a lot of research out there showing that human biases come into play when people are grading essays. But some states are still using automated essay grading systems where the training data consists of essays graded by humans. This is essentially treating the human scores as ground truth when we know that they're not ground truth. Once again, there are best practices that can be followed in this data labeling and pre-processing stage. So first, you should check whether you're introducing biases by discarding data. For example, suppose your data points contain gender. What might happen if you just throw away data from anyone who declines to report their gender? Relatedly, you could be introducing biases by bucketing values. For example, if you're bucketing by race. Not everyone identifies with only a single race. Third, you should check whether any software that you're using for pre-processing might introduce biases. For example, you may want to run machine translation on text as a pre-processing step. But we've already seen that machine translation systems can do things like swap the gender of pronouns. Similarly, you should check any labeling or annotation software for biases. And finally, you should consider whether the human labelers who are in the loop here might introduce bias, as was in the case with the automated essay grading. Many of these data-related strategies can be at least partially addressed with better data-related standards and documentation. This isn't a new idea. So other industries have been in exactly this place before, including the automobile industry and the electronics industry. These days, in fact, every electronic component, ranging from the simplest resistor all the way up to the most complex microprocessor, has a corresponding data sheet detailing all of its operating characteristics, recommended usage, and other information. Inspired by data sheets for electronic components, Hannah and I, along with some of our amazing collaborators, have a project called Data Sheets for Datasets. We propose that every dataset, model, or pre-trained API should be accompanied by a data sheet that documents its creation, intended uses, limitations, maintenance, legal and ethical considerations, and so on. We view this as a way to surface potential biases, making it easier for teams to develop more fair machine learning systems, though it has benefits that go far beyond fairness, too. This is a prototype of a data sheet that we made for labeled faces in the wild, a well-known computer vision data set consisting of images of faces. It's hard to see from this slide, but the data sheet contains a variety of information about the data set, including a breakdown of images by age, gender, and so on. To help teams construct data sheets for their own data sets, we've put together an initial set of questions that cover different types of information that we think belong in a data sheet. The questions are divided into 7 categories listed here: so motivation, data set composition, the collection process, data pre-processing, distribution, maintenance, and legal and ethical concerns. And each of these categories has about 5 to 10 questions. For example, in the composition category, there are questions about the data points themselves, as well as questions about recommended data splits and evaluation metrics. In the collection process category, we have questions about who was involved in the collection process, the time frame over which the data was collected, and whether the data is sampled from some larger population. The datasheets concept has been pretty well received so far, but of course, in order to turn it into a standard engineering practice, there are a number of implementation challenges that have to be addressed. I won't go into details here, but we and others throughout Microsoft are currently working on addressing these challenges and refining this concept for wider use. Okay, so that's enough about dataset construction. Let's move on to model definition. So what is a model? Well, a model is just a mathematical abstraction of some part of the world. For example, we might assume that the price of a house is a linear function of the number of bedrooms, the number of bathrooms, the number of square feet, with a little bit of random noise and variation added. By its very nature, a model is simpler than the world. So choosing a model necessarily means making some assumptions. What should be included in the model and what shouldn't? How should we include the things that we do decide to include? And sometimes these assumptions can privilege some people over others. Consider predictive policing. A predictive policing system may make predictions about where crimes will be committed based on historic arrest data. One implicit assumption here is that the number of arrests that are made in a location is an accurate proxy for the amount of crime in that location. This doesn't take into account that policing practices can be racially biased or that there may be historic over-policing in less affluent neighborhoods. As another example, it's common for teachers to be evaluated based on factors including their students' test scores. As highlighted in a federal lawsuit, this assumes that students' test scores are an accurate predictor of teacher quality. But of course, this is not always the case, and a good teacher should do more than just test prep. There are also implicit assumptions in the structure of the model chosen. So in this toy example, in which individuals are represented by two features, we've got a majority population and a minority population that look fundamentally different from each other in terms of these two features that we've chosen. In this case, there's no simple linear classifier that would work well for both. This means that you probably don't want to be using a simple linear classifier on these features. Maybe a nonlinear model would be a better choice in this situation, or maybe we should just be looking for a different set of features altogether. Finally, harms can be introduced by assumptions that go into the objective function. Here I'm showing Bing image search results for the term boy on the left and the term girl on the right. These clearly look very different from each other. This probably comes from the fact that Bing, like all search engines, is optimizing for clicks, among other things. This example shows just how hard it can be to fix fairness issues. In different circumstances, the word girl may be referring to a child or a woman, and users search for this term with different intentions. Right? So in this case, for reasons you can imagine, one of these intentions may be more prevalent than the other. So when defining a model, we should follow these best practices. First, clearly define all of our assumptions about the model. Second, try to identify any biases that are present in these assumptions. The ability to use number of arrests as a proxy for amount of crime is an assumption and should be questioned. Third, check whether the model structure introduces biases. Next, check the objective function for any unintended effects. We're making an assumption when we design a search engine or a website to optimize clicks, and assumptions like these should be questioned in the context of whether they might introduce biases. You might also consider including some notion of fairness directly in the objective function if this is something that it's appropriate to do in your setting. Okay, let's move on to the training process. So the training process is the stage of the pipeline where we optimize or learn the parameters of a model. The weights W1, W2, and W3 in this example that I showed earlier, based on the training data that you have in your objective. So there's some good news here. Once you've settled on your data set, your model, and your objective, the actual training algorithm that you use is probably not going to introduce any additional bias. We see this as a common misconception, actually. You generally don't have a biased algorithm, at least not a biased training algorithm. The problem usually comes more directly from the model you've chosen or the objective or these other factors that we've discussed. Okay, so the testing phase of the pipeline is your opportunity to check for biases and potential harms. And problems can arise if you don't have the right testing data or the right metrics in mind. For example, let's return to this research paper that showed that commercial gender classification software performed poorly on women with dark skin. This is the kind of problem that can be caught during the testing phase. If you want to build products that work well for everyone, then you should explicitly be testing products' performance on different segments of the population. In the case of the COMPAS recidivism prediction tool, there was some internal testing, but external audits still revealed unfairness in this system. So to talk about why, we need to get a little bit into metrics. I'm going to spend just a couple of minutes going through some different metrics here just to give you an overview of what the landscape looks like. Fairness metrics are currently most well-defined for classification problems. To simplify things, I'm going to focus only on binary classification in my discussion here. And the main thing that I want you to take away from this is that there are a bunch of fairness metrics, and these metrics are more or less appropriate in different circumstances. If you want to learn more, there's a great tutorial by Arvin Narayanan from FatStar 2018 that you can find online. Okay. So to define the fairness metrics that are typically considered for binary classification, it's useful to start with the idea of a confusion matrix, which many people might already be familiar with. Here I'm showing a confusion matrix for a hiring scenario. We have some applicants who are qualified for a job and some applicants who are unqualified. Our machine learning algorithm chooses to hire some of these applicants and to reject others. Qualified applicants who are hired are true positives, while unqualified applicants who are rejected are true negatives. Your algorithm is getting both of these right. Meanwhile, qualified applicants who are rejected are false negatives, and unqualified applicants who are hired are false positives. A confusion matrix simply tells us how many applicants fall into each of these four buckets. And these four numbers that are given by a confusion matrix can be used to compute various standard machine learning performance metrics like accuracy and precision. So rather than considering only a single confusion matrix for a whole set of applicants, we can choose to break things down by demographic and compute separate confusion matrices for, say, our male applicants and our female applicants. To be concrete, we filled in one example of what these matrices might look like with some numbers here. Notice that in this example, there are 100 men and 100 women in total. For both men and women, the system makes correct decisions on 75 out of 100 applicants. 60 qualified men are hired and 15 unqualified men are rejected. These are all correct decisions. Meanwhile, 15 qualified women are hired and 60 unqualified women are rejected, also correct decisions. So the accuracy is the same in both of these cases, but the system makes different types of errors on these two groups. So let's see how a few different fairness metrics play out in this case. So the first fairness metric that you might hear about is demographic parity. Demographic parity is based only on classifier output and doesn't take into account true labels at all. It says that applicants should have about the same probability of being hired regardless of whether they're male or female. So the ratio of hired applicants to total applicants should be the same for each group, or at least approximately the same for each group. If you happen to have heard of the EEOC's 80-20 disparate impact rule, this is a very similar idea. So in this case, the system does not satisfy demographic parity because 80 of 100 men are hired while 20 of 100 women are hired. But, maybe you might say this is okay because in this particular example, more of the men are qualified than the women. Just as an aside, demographic parity is perhaps the first metric that you would want to look at when evaluating an automated hiring system like the one that Amazon proposed. So going a bit deeper, predictive parity takes the true label into account as well as the classifier output. It looks at the probability that an applicant from some group is qualified given that you've chosen to hire this applicant. And it says that this should be the same or about the same for both of these groups. In this case, the system does satisfy predictive parity, since for both of these groups, 3/4 of hired applicants are qualified. Now, false positive rate balance is another metric that says that false positive rates should be the same for both groups. That is, the probability that an unqualified applicant is hired must be the same or about the same for men as it is for women. In other words, your classifier should treat all unqualified applicants the same regardless of whether they're male or female. In our example, the false positive rates are different, with a substantially larger fraction of unqualified men being hired than unqualified women. False negative rate balance is essentially the same thing, but for false negative rates. It says that the probability of a qualified applicant being rejected should be roughly the same for men as it is for women. In other words, the classifier should treat all qualified applicants the same, regardless of whether they're male or female. Again, in this example, our false negative rates are different, with qualified female candidates much less likely to be hired than qualified male candidates. You may sometimes hear the term equalized odds come up, and in the context of binary classification, this simply means that you simultaneously satisfy false positive rate balance and false negative rate balance, basically treating all similarly qualified candidates similarly. So this notion of equalized odds that I just mentioned is effectively the fairness metric that ProPublica considered when it was auditing the COMPAS system for racial bias. In other words, they asked whether COMPAS makes similar errors in terms of both type of error and quantity of error for black and white defendants, and indeed they found that it does not. Because of this, they said that the system was racially biased. In response, Northpoint, the company that built COMPAS, argued that COMPAS does satisfy predictive parity and is therefore fair. So there's a lot of back and forth about this and about why the system couldn't just satisfy all of these metrics. But it turns out that things are not so easy. In fact, it turns out that it's mathematically impossible for a system to simultaneously satisfy predictive parity, false positive rate balance, and false negative rate balance. Any system that satisfies two of these properties must necessarily fail to satisfy the third. This impossibility theorem was really at the heart of the public debates around COMPAS and racial bias. As long as Northpoint requires that COMPAS satisfy predictive parity, it can never satisfy equalized odds. So what should Northpoint do in this situation? Well, this is a tough question. But people have made the argument that given the impact of these decisions on people's lives, equalizing false positives and false negative rates between races is more important perhaps than calibration. So equalized odds is arguably a better measure here. Okay, so what are some best practices for testing? First, you should ensure that the test data set matches the context in which the system is expected to be deployed, and ensure that the test data has sufficient representation in it. Doing these things would have helped developers identify the performance imbalance in gender classification systems before these systems were ever deployed in the first case. Of course, all of the standard risks of overfitting apply here. So I just want to mention you should be aware of this if you find yourself really relying on one particular test data set and tuning your model to be fair on one particular test data set. Next, you should involve diverse stakeholders who represent multiple perspectives to ensure that you're testing for the right things. The Diverse Voices project from the Tech Policy Lab at UW has created guidelines for making tech policy more inclusive by having short, targeted conversations with panels of people who have diverse viewpoints. Similar ideas could easily be used in product development as well. Additionally, you should clearly state all of the fairness requirements for your system and use appropriate metrics to ensure that your requirements are met. But of course, you should keep in mind here that there are trade-offs that need to be made with any of these metrics, and that, again, many aspects of fairness are just not possible to capture with metrics at all. As Hannah mentioned before, fairness is a socio-technical concept, and we can't always use quantifiable metrics to capture it. Okay, so moving on to deployment. The most common issue here is the one that I mentioned briefly a few minutes ago. That the deployment population is somehow different from the population that you either implicitly or explicitly assumed that you would have. That is, your deployment population is different from the population from which your training and testing data were generated, or the population that you had in mind when you were defining your model. A common example is collecting training data from people in one country, say the US, and then deploying a system in other parts of the world. There's actually some interesting research way back in 2011 that looked at available face recognition tools and showed that the location where a face recognition system was developed had significant impacts on its performance on different populations. Specifically, systems were substantially more accurate on faces from the same geographical region that the system was developed in. When deploying a system, you should double check that the data source matches the deployment context, and keep an eye out for discrepancies as you collect more data on your system's performance. You should also monitor your fairness metrics for any unexpected changes. At this point in the pipeline, it can also be advantageous to invite diverse stakeholders to audit your system for potential biases. For the initial audits, it's really better to be in control of this process yourself. You don't want to be in a situation where someone from the outside audits your product for fairness before you get a chance to. Remember, it was external audits that revealed that commercial gender classification software had different performance on different groups. Finally, you should monitor user reports for any potential fairness issues. All right, so finally, there's the feedback stage. This is something that's discussed a lot in the context of predictive policing and hotspots. So as we've already discussed, predictive policing systems operate under this assumption that more arrests in an area means more crime. This can create a feedback loop or a self-fulfilling prophecy. More officers are deployed to neighborhoods where more crime is predicted. And this ends up leading to more arrests, which leads to higher crime being predicted in the future, and to even more officers being deployed to these areas. Adversarial feedback can also be an issue here. A few years ago, when Microsoft released the social chatbot Tay, there were groups who took advantage of Tay's use of feedback in order to adversarially insert biases and other harms into the system. The best practices here at the feedback stage overlap heavily with those for the deployment stage, which makes sense because the line between these stages can be pretty fuzzy. You should continue to monitor the match between your training data and the data that you're seeing in the wild, continue to monitor fairness metrics, and continue to monitor user reports too. Monitoring appropriate fairness metrics could surface that predictive policing systems are getting more biased over time. You should also monitor users' interactions with your system. And if necessary, you might consider prohibiting some types of interaction altogether. For example, for a chatbot like Tay, in addition to monitoring things, it may be necessary to actually restrict certain types of feedback, especially because in this case, the severity of the harms that can arise is high. All right, so we have made it through the machine learning pipeline. We've talked about both where harms come from and strategies that you can take to mitigate these harms. And with that, I'm going to turn things back over to Hannah.
All right, so for the last part of this talk, I'm going to tell you about some recently developed software tools for detecting and mitigating harms. Over the past few years, the academic machine learning community has turned its attention to the topic of fairness in machine learning. And while this graph here isn't strictly accurate, over the past few years, we've seen a massive increase in the number of papers published on this topic. Spurred by this increase, we've also seen researchers and practitioners start to develop software tools that implement the ideas put forward in these papers. So I want to run through a handful of these tools with you, just so that they're on your radar. Okay, So the tools I want to tell you about fall into a couple of different categories. The first category is auditing, both auditing data sets to uncover potential biases and auditing the outputs of systems to see if those outputs are fair according to the kinds of metrics that Jen told you about earlier. The first tool I want to highlight is Equitas, which was developed by researchers at the University of Chicago's Center for Data Science and Public Policy. Equitas consists of a web audit tool, a Python library, and a command line tool for auditing the outputs of systems for allocating opportunities, resources, or information according to some of the metrics that Jen told you about previously, plus a couple of other metrics as well. It's pretty easy to use and generates really nice bias reports, though it is a little limited in what it can do. The second auditing tool that should be on your radar is IBM's AI Fairness 360. This tool was recently released and received a lot of attention in the media. Like Equitas, it's focused specifically on systems for allocating opportunities, resources, or information. And it does implement more fairness metrics than Equitas, though it's not entirely clear how commonly used some of these other metrics are. One nice thing, which I haven't played around with yet, is that it implements some metrics for assessing individual fairness, unlike Equitas. Before I move on to the next category of tools, I do want to again emphasize that fairness is a fundamentally socio-technical challenge. So these tools are not be-all and end-all solutions and are only appropriate in certain particularly limited circumstances. Specifically, they focus on harms of allocation and certain types of quality of service and not on other types of harm. Moreover, there are many aspects of fairness, such as justice and due process and so on and so forth, that aren't captured by metrics that look only at parity in decision-making. And finally, as Jen told you, it's impossible to simultaneously satisfy all of these fairness metrics, except in very rare circumstances, which means that if you try to improve your system with respect to one metric, you might make it worse with respect to another. As a result, it's important to discuss which metrics are most important to prioritize in a given context, to discuss the limitations of those metrics, and then to make trade-offs, and to examine the impact of those trade-offs. But these tools do at least give you a way to explore these various different options. Great. So the second category of tools that I want to tell you about is fair classification. So tools for developing fair systems for allocating opportunities, resources, or information by specifically making decisions of the form loan, no loan, hire, don't hire, bail, no bail, and so on. There's been a lot of research in this space, focusing on pre-processing data, post-processing system outputs, and all involving some notion of fairness. Sometimes this notion of fairness is even included in the classifier's objective function. I'm not going to talk about all of these today, but instead I'm going to focus on one method that I developed recently with some collaborators. So this method takes the approach of including some notion of fairness in the classifier's objective function. And the typical way to do this is typically to first choose an appropriate fairness metric. Then the machine learning goal becomes one of maximizing classifier accuracy while minimizing unfairness according to the chosen metric. So in other words, the classifier's objective function has two parts: classifier accuracy and the chosen fairness metric. There are two technical challenges to this goal. First, choosing the fairness metric, and two, learning an accurate classifier subject to the constraints imposed by that metric. Our method focuses specifically on the second one of these challenges. We've shown that for a wide range of fairness metrics, fairness-constrained classification can be reduced to cost-sensitive classification, a well-studied class of problems for which there are many off-the-shelf tools. There are several benefits to this approach. First, our method works with many different fairness metrics, and this means that there's no need to start again from first principles to switch to a different metric. Second, our method is agnostic to the form of the classifier and the training algorithm. As a result, it works with a wide range of existing classification methods, such as neural networks trained with backprop, ridge regression solved in closed form, or support vector machines trained with stochastic gradient descent. Taken together, these 2 points mean that our work kind of puts a stop to this cottage industry of papers that each consider a single classification method and a single fairness metric. Another benefit of our method is that it doesn't require deployment time access to attributes like race or gender. And this is great for 2 reasons. One, as I explained earlier, many teams have no such access to individual level attributes. And 2, this is likely important for mitigating disparate treatment concerns. Finally, unlike other approaches to fair classification, our method is theoretically guaranteed to find the most accurate classifier subject to the chosen fairness metric. We've also empirically demonstrated this last benefit using a variety of data sets from education, employment, and criminal justice, showing that we achieve better accuracy fairness trade-offs than other fair classification approaches. And we've released an open source Python library that implements our method. While I'm talking about this, I do want to point out that IBM's AI Fairness 360 also implements 3 methods for fair classification, though the method I just told you about is more general and more flexible than any of these 3 methods. Before I move on, I want to highlight some points to consider when thinking about fair classification. First, you need to choose an appropriate fairness metric. Of course, because there are trade-offs between metrics, it's still important to assess other fairness metrics in order to examine the impact of these trade-offs. Second, people, myself included, often talk about the accuracy fairness trade-off, implying that by prioritizing fairness as well as accuracy, you might end up with a less accurate classifier. This may be true with respect to some test data set, but it's important to think about your deployment context, as Jen mentioned, which may be different to your test data. In particular, you may actually end up with better accuracy at deployment time by including fairness in your classifier's objective function. You can kind of think about this as a form of regularization. Finally, I want to again note that there are many aspects of fairness that aren't captured by these kinds of metrics, and that there are many types of harm that can arise in contexts other than classification. Next, I want to talk briefly about mitigating stereotypes in word embeddings. So earlier I told you that researchers at Princeton found that translating he is a nurse and she is a doctor into Turkish, a gender-neutral language, and then back into English yields the stereotypical she is a nurse and he is a doctor. Jen then told you that this harm likely occurred because of societal biases that are present in the text data used to train machine translation systems. More specifically, many translation systems rely on word embeddings generated by embedding methods such as word2vec, which embeds words into a low-dimensional space based on their surrounding words in a corpus of documents. Our colleague Adam Kalai and his collaborators showed that word2vec, when trained on news articles, exhibits strong male-female gender stereotypes. For example, man is close to programmer, while woman is close to homemaker. These stereotypes are then propagated to any downstream systems, such as translation systems, that use embeddings. Adam and his collaborators also showed that you can, in some circumstances, remove such stereotypes by identifying a definitional dimension and an orthogonal stereotypical dimension in the low-dimensional space, and then projecting words embeddings down so as to eliminate the stereotypical dimension. They also released an open source Python library that implements this. So there are a handful of points to consider, though, when thinking about using tools for mitigating stereotypes in word embeddings. First, this approach works with pre-trained word embeddings, so you don't have to train your own word embeddings to use it. That said, it is harder to integrate into systems that simultaneously learn embeddings at the same time as performing some downstream task. Not all subpopulations have an obvious definitional dimension, which means that it's harder to remove some kinds of stereotypes than others. In part because of this, and in part because stereotypes relate to a broad cultural context, it's impossible to guarantee that you have removed all possible biases. And finally, it's really important to assess the effects of mitigating stereotypes on the performance of any downstream systems that use the embeddings. Great! So we did it. We covered all 4 topics. And hopefully we've now given you a fairly comprehensive overview of fairness in machine learning. Before we conclude, though, I do want to briefly talk about open questions. As we've emphasized throughout this talk, fairness is a fundamentally societal concept, and one that is still pretty new to the tech industry. As a result, there are a lot of open questions and not a lot of easy answers. I therefore want to briefly note some of the open questions that I think are particularly important, just so that you're aware of them when you're thinking about this stuff. So, I mentioned earlier that Jen and I, along with our colleagues Hal Dalmay and Miro Dudik, as well as our awesome intern Ken Holstein, spent last summer conducting the first systematic investigation of industry teams' challenges and needs for support in developing fairer machine learning systems. I want to very briefly tell you about some of our main findings because I think they illustrate some of the most pressing open questions. Just so you know where these findings came from, to conduct our study, we followed established methodology from human-computer interaction. Specifically, we started by conducting a series of initial semi-structured interviews with 6 product managers, each responsible for a product in a different domain. Based on the themes that emerged from these initial interviews, we then conducted a second round of interviews with another 29 practitioners. And in total, we ended up interviewing 35 people from 25 different teams across 10 major technology companies. And as you can see from this slide, these teams span a variety of domains, from adaptive tutoring to multimodal sensing to web search. Where possible, we tried to interview multiple people from the same team in order to hear different perspectives on the team's challenges and needs for support. In addition to our semi-structured interviews, we also conducted an anonymous survey of 267 industry practitioners, working in domains ranging from robotics and cyber-physical systems to natural language processing, in roles such as social scientist, data labeler, program manager, researcher, and data scientist. We found that a number of themes emerged from our semi-structured interviews, which were then further reinforced by the data from our anonymous survey. I'm not going to talk through these in detail, but I want to highlight some of the needs for support. First, we found needs for support in auditing systems for biases in a diverse range of applications beyond allocation, classification, and prediction. We also found needs for support in creating fairer data sets, so how best to do this in practice. We found needs for support in identifying relevant subpopulations, as I mentioned earlier. And we found needs for support in detecting biases with access only to coarse-grained, partial, or indirect information. And I think these needs highlight some of the open questions in this area that we really, as a community, need to start thinking about addressing. All right, so to wrap up, I want to end with some key takeaways. I'm going to structure these takeaways around 3 calls to action. These calls aren't comprehensive, but they do highlight some of the most important dimensions to keep in mind when thinking about fairness. First, prioritize fairness at every stage of the machine learning pipeline. Fairness really should be a first-order priority, just like security and privacy. But in order to make this happen, we can't treat fairness as an afterthought. Rather, we have to actively think about it, starting right from the task definition all the way to deployment and feedback. Second, involve diverse stakeholders and multiple perspectives. Fairness in machine learning is a fundamentally socio-technical challenge that can't be addressed by computer scientists or developers alone. We have to involve social scientists, lawyers, policymakers, diverse teams, end users, and all kinds of other stakeholders in these conversations to make sure that we're answering the right questions. And finally, adopt a growth mindset and learn from failures. It's just not possible to solve fairness. We can't de-bias our models or our data sets or guarantee that they're bias-free, and technology is just never neutral. Fairness isn't a one-shot process either. We will make mistakes. Let's therefore anticipate them as best we can, embrace them, and turn them into something positive. That is, learn from them and let them contribute to our successes. Thank you.